Hello, I'm here to present my group's project for statistics. I'm Christopher DeSisto, and my group members are Austin Frost, Evan Riley, Justin Falvo, Sylvania Nunez, Michael Schlossman, and Nicholas Mathern. The statistical topics that we will be covering in this presentation are sample size, mean, standard deviation, confidence interval, and normal distribution. These are some of the most frequently used methods of data analysis in the engineering field. Our group has chosen to create a real-world engineering scenario in which some of the statistical topics mentioned previously will be utilized. From this point forward, I will be presenting as a statistician from the company Half-Inch Ball Bearings Incorporated. As you might assume, the company produces ball bearings, and they will run into an issue that statistical analysis can help solve. In a perfect world, machines would produce parts of the exact same size repeatedly without error. However, we do not live in a perfect world. Here at Half-Inch Ball Bearings Incorporated, we strive to produce the best ball bearings the world has ever seen. Our design is flawless, but the machines we use to produce them are not. As you know, the inner diameter of the ball bearings we produce is 0.5 inches. Our machines, however, do not produce the ball bearings with consistent diameters. Although each one is very near 0.5 inches, we weren't sure how close the average is, and if it's close enough to satisfy our customers. In order to determine the accuracy of our machines, we decided to run a statistical analysis. Ultimately, our goal was to create a normal distribution of the ball bearing diameters as well as a confidence interval to determine where the true average lies. By having a proper estimate of the average and normal distribution, we will be able to determine how likely our machines are to produce inadequate ball bearings. By creating a confidence interval, we will be able to estimate the true average diameter of our ball bearings. We claim 0.5 inches. The true average, however, may not be 0.5 inches. If this is the case, we would have to adjust the parameters of the machine. Confidence intervals are also heavily dependent on sample size. The goal is to have a very small interval, and the greater the sample size, the smaller the interval. The formula for a confidence interval is mu plus or minus z sub alpha over 2 times sigma over the square root of n, where mu is the sample mean, z sub alpha over 2 is the z value for the given confidence percentage, sigma is the sample standard deviation, and n is the sample size. Normal distributions are incredibly common in statistical analysis. Normal distribution relies upon standard deviation. The standard deviation is the average distance from the mean, and the values that are multiple standard deviations away from the mean are much less common than values that are closer to the mean. As you can see in the graph, the further away from the mean you get, the smaller the concentration of values. In an ideal situation for us, nearly 100% of all ball bearings we produced will be within the desired range. Looking first at the confidence interval, we found with 95% confidence that the true average diameter lies between 0.499 inches and 0.505 inches. The desired average of 0.5 inches lies within the interval, which means the true average is at least somewhere very near 0.5 inches. This shows that our machines will regularly produce ball bearings of the proper size. However, it fails to show just how many ball bearings will be of an inadequate size. The normal distribution that we have created allows us to see just how likely our machines will produce ball bearings of certain diameters. The accuracy of the distribution relies heavily on the sample size. Since we sampled 1,000 ball bearings, the distribution should be quite accurate. The distribution is centered at the average diameter of our 1,000 ball bearings, 0.502 inches. A normal distribution implies that the majority of all ball bearings will have diameters closer to the average, and we can see the proportion of ball bearings that will be below or above the average. As we get further away from the average, a smaller amount of ball bearings would be produced of that size. As you know, we need our ball bearings to be 0.50 inches, which means 0.494 is too small and 0.505 is too large. Looking at the graph, the shaded area is the desired range of diameters. Based upon the data, there is very small likelihood of producing ball bearings that are too small, less than 1%. The concern is on the other end, though. As you can see, a decent proportion of the ball bearings, approximately 5%, are too large. This means that 5% of all ball bearings our machine produce are inadequate. Based upon these results, we recommend that you adjust the parameters of the machines to produce slightly smaller ball bearings. This could reduce the 5% to around 2%. 2% is still quite high though. The only way for us to produce nearly 100% accurate ball bearings is to either find a more reliable machine or make it aware to our customers that our ball bearings are 0.5 inches plus or minus 0.003 inches. This should encompass nearly 100% of all the ball bearings we produce. Thank you.